Okay. So we are back to 5.4. First of all, the formula is just that. It's a formula. It looks very hard. Hey guys, hey. It looks very hard. It looks very complicated. It is complicated, okay? But after all, it's just a formula. You got 5 variables, you plug in the variable, and you calculate. And it's simple as that. So, the call is simply equal to S0 is the current price multiplied by 1 probability. It's the probability, and I will explain in a minute, and I'll explain the 1 in a minute. This is just short notation. D1 is a short notation and is a normal distribution. So it's the cumulative normal distribution of D1 minus X is the exercise price times the E minus RCT. Let me see, is it a big or a small t? Big T. Times, it's got to be ND2. Okay, so N of D is cumulative normal distribution. Cumulative normal hello. All right. So, again, for you, N is the cumulative normal distribution. I'll explain it in a minute. D1 and D2 are special terms. So, what does cumulative mean? It means the following. If this is 0, and this is the like a normal distribution with a bell shape. I'm just picking a number to illustrate what's a cumulative. And this is some number, let's say 2.7. Okay, I'm just picking a random number, 2.7. The cumulative normal distribution is this area over here. Is that the probability of X is less than 2.7. In other words, what's the probability that you will observe the variable to be lower than 2.7? Okay. So, in our case, if this is D1, it simply is the probability that X, in our case, it's going to be the price or the stock, will be less than D1. That's it. So it tells you the probability to the left of the variable, to the left of the variable. This is the cumulative distribution. We call this type of, in mathematics, in every elementary course, you call this distribution function. The distribution function tells you the probability that the variable will be lower in a certain cutoff point, okay? And sometimes we just say yeah, okay? So that's what the continuous. D1 is a simple formula. It's actually normalizing. What it does, it takes a normal distribution and it takes the returns and it normalizes the returns. So it becomes log. It's very looks complicated. Log of S0 over X. So first, it normalizes the price of the stock to the exercise price. So if the price of the stock is 110 and the exercise price is 100, it will simply be a ratio of 1.1, okay? Here of 1.1. Here, if S0 is respectively 90 and X is 100, that ratio is going to be 0.9. In other words, you don't want the difference between between the stock price and the strike price. You don't want to say, oh, the difference is $10. We want to say, oh, the difference is 10%. It is 1.1, okay? So you don't want to express it as a difference. You express it as a ratio. The ratio will get to normalize things. Kind of like the ratio between 90 and 100 is the same as 120 and 200. It's just going to scale things up. So you're not using differences, you're using ratios. So that's the one part. Plus, let's see what else we got in here. RC plus sigma squared. Well, RC is the expectation, and sigma squared is the variance. That's a very, very standard formulation of the normal distribution. And you multiply this by t. So sigma is the continuous variation. So sigma represents what we call, as I wrote it out there, the variance. But the variance is on a continuous basis. So when the variance is a continuous basis, you need to multiply by t to get the variance for the whole period, okay? So if it's like, I'm just picking a number, 1%, the variance for 1 day, well, for 10 days, it's going to be 10%. For 50 days, it's going to be 50, okay? For 100 days, it's going to be 100, okay? And then the standard deviation is going to be the square root of that. I'm going to provide a few examples. But here, t simply tells you, hey, we have some expectation for the return, and we're going to throw in the variance to see what happens. And then you're going to normalize this whole thing by the sigma, which is again the standard deviation, the variance, and you got the square root of t. So you're gonna re-normalize back to the, so square root of t, you're gonna be getting back the variance. Okay, you're going to be getting back the variance. I'm going to show you a few examples so you can see what happens. It's fairly easy and fairly straightforward. And D2 is simply D1 minus sigma square root of t. Sigma is annualized and it has to be continuous. annualized volatility of continuous. So whatever is the continuous volatility, you have to annualize it, okay? But you annualize the continuous volatility, in other words, the continuous return. And the RC, again, this C means continuous. So risk-free rate, continuous, on a continuous basis. And that's what I did when I was explaining in the previous section the continuous returns. If it's 10%, becomes log of 1.1. Okay? Okay. Now they got this whole thing here about standard normal probabilities. That's section number 4. So this is essentially 5, 4, 1. It's just what the formula is. Now the explanation is on normal distribution. When you have a normal distribution, it's got some very, very nice properties. You've all studied them. When you take a range of minus sigma to plus sigma, okay, I'll use this. The probability is about how much? In other words, if you take a normal distribution and this is the sigma over here, and this is the sigma over here. This representing from the mean minus sigma, and this representing from the mean plus sigma. And here we just put in 0. Okay, we just normalize it to 0. This area here is how much? How much is the area of plus minus 1 sigma? Anybody? Do we have engineers here? At least? I mean, economists wouldn't know this, but engineers? What's the percentage, the chance? Huh? Yeah, we like to round it up to 66. It's a nice rounding. It's a 66, okay? Oh, what's the average height of a type person? About, roughly. What's the average height? Both men and women at the same time. About what? 166? Hmm? Hmm? How much? Hmm? Okay, there it is. So, mu equals 165. What will be roughly about the standard error? So, you take a whole bunch of 100 guys. Okay, let's take them between the ages of 18 and 25. Because now the younger guys are a little taller than their parents, right? Because you're well fed with beef and chicken and all the other meat, right? So you're taller. So we're going to say that the sigma is about, I'll just do it roughly 5 centimeters. 5 centimeters, okay? So that's the sigma. Now the question is, how many people do we expect in this classroom to be over 170? How many people? Why is everyone, so what's the calculation? How do we calculate it? You can use, the pen and the calculator. What is it about? How does it work? Well, this one here is 165. 1 sigma is going to be 170. Here is 160. Okay? So, if this is 66%, what is the chance here? What is the chance here? Number? Anyone? Number? If this in the middle is 66%, what's the chance on the left? Hmm? Number, I want to hear one number. What's the percentage? Huh?
17.
Okay, 17. So, 17% chance of being less than 170, and it's going to be 17% chance of being less than 160, 17% chance of being over 170. Well, 17%, what is 17% in here mean for 27 students? So for 27 students times 17%, what is it about equal? So it's about 1/5, about 5. So we expect about 5 people to be over 170, right? And we expect about 5 people to be less than 1. So 5 people will be 170 plus, and it's going to be 1 less than 160. Okay, raise hands everyone who's over 170. Ooh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got 11 people over here. Well, all the people, mostly, less than 160. Less than 160. 1, 2, 3, 4. Huh? 1, 2, 3, 4. Is it 4 or 5? 4 or 5. All right, so we can make a conclusion. What's the conclusion out of here? Either the height tall is not normally distributed. That's number 1. Number 2, why is this occurring? What's really the problem here? Why we get 11 versus 4? Well, we're supposed to get roughly equal. Where's the error coming from? Where's the error coming from? Not the average. From the representative sample. We probably have a lot more boys than girls. Okay? So the average is based on 51% women and 49% men. Okay? It's represented on equal number of men and women. But in every country, women are always a little bit more, like 1% more. Okay? So, here the class is not 50-50. And if boys are taller, obviously we're going to get a little bit of a bias. In other words, our sample is not representative of the average population because we don't have 50% boys and 50% girls, okay? So that's the one thing. And because you're all between the age of 22 and 30 on average, right? Probably your average is not going to be 165, there's going to be a little bit higher. So we got a little bias because you're younger, and we got a second bias because you're males, okay? Well, what can we do first to normalize things? So we say that the distribution is a normal, standard normal, is a distribution Z, which is normally distributed with a mean of 0 and a standard, okay, well, we'll just say variance of 1. And if it's a variance of 1, standard deviation will be also 1, is 0, 1. So when we have any normal distribution, we always like to normalize it. To normalize it means we will subtract of it the mean, and after we subtract the mean, we're going to divide by the variance. And when you subtract by the mean and divide by the variance, you're going to get a 0, 1. And when you get a 0, 1, it's very easy to see the probabilities. And the probabilities are a simple table, standard normal probabilities. Standard normal probabilities are a simple table. So now we need to see how to normalize. Let's try to do this little thing here. Probability of minus sigma plus sigma, meaning 1 sigma is going to be 66%. The probability of 2 sigma on the plus side and 2 sigma on the minus side is how much? So, for 1 sigma, it's 66%. For 2 sigma is how much? 95. Well, we like to round it to 95. I mean, it's about 95. So, 2 sigmas will include 95% of the population. And 3 sigmas will include how much? 99%. Now, let's try for you. On my textbook, the page is 137. We got a little table, 137, right? Camera, zoom in, right? And on 137, we want to look up 2 sigmas up and down. We want to try to find out the exact value. Is it done? Is it okay? Okay. So let's try and look up for 2 sigmas. What's the probability for 2 sigmas? What's the table saying? What's the table saying for 2 sigmas? What's the table saying for 2 sigmas? Anybody? Anybody? 2 sigmas. Oh. When we say 2 sigmas, we simply say z equals 2. And for z equal 2, what's the probability? What's the prob value? What's the cumulative probability? Come on, guys.
0.9772.
Yeah, 0.9772. Okay. Anyone? You can guys read it off the table here. 2.0. You look here. Everybody, look over here. 2.00. 0.9772. Okay? So, if that's the case, it's like this. This probability all the way up to here is, for here it's 0, here it's 2, is 0.9722. So, now the question is, what is the probability of the, we call it the right tail. What's the probability of the right tail? So the probability of the right tail, for the one tail, what is it? 1 minus this. So 1 minus this will give you 8. What is the next one? 2, 2, 0, 0. So the probability of being on the right tail is 2.28%. That's the right tail probability.
Is that both tails?
Huh?
Is that both tails?
Well, I don't think so. So that's the right tail probability. Now, when you take the left tail, both tails, it's got to be double. So both tails, it's going to be 4.56%. Okay? So the two tails will be 4.56. So plus minus 2 sigma, minus 2 sigma, plus 2 sigma. What's the exact probability? The exact probability is? What's going on? The probability of the right tail is 228. The probability of both the right tail and the left tail is 4.6. What's the probability to be between them? What is it? 95.44%. So, the exact number of plus minus 2 sigma is 95.44, which we conveniently round to 95% for easy, okay, thinking. And the same thing with 3 sigma is 99%. Well, what's the exact number for 3 sigma? What's the exact number for 3 sigma? For 3 is 0.9987. So for 3 is 9987. Okay? What does it mean? Means 0.13, huh? 0.13. So it's actually way more. 3 sigma is way more than that, okay? So this means that it's, for the 2 is 0.26%, okay? So it's like 99 point whatever, 99.7 something, all right? So it's just a simple calc. You can do, what about 1 sigma? Let's calculate 1 sigma. Anyone, calculate 1 sigma. How much is 1 sigma? 0.8413. 0.8413. That's the cumulative distribution from minus infinity to 1 sigma. So what's the right tail? What's the right tail? The right tail is 16 is about 15.
15.87.
15.87. Okay. So 15.87. So for 2 tails is how much?
31.74.
So it's about 32%. So it turns out that according to this calculation is about 68%. Well, 67. Right? 67%. About. Okay? So we like to think that plus minus 1 sigma incorporates 2/3. 2/3 is like to think like 66.6. It's not exact, but it's a very good. It gives you an error less than 1%. Okay? So when you work with 27 people or when you work with 100 people, the mistake is negligible. So this is how This is about normal distribution, and this is the so-called Z distribution. So the question is how we normalize. Well, the normalization actually goes by simply subtracting the mean and then dividing by the, well, we gotta see, dividing by the standard deviation. You want to get, or divide by the variance to get, you divide by the standard deviation to get the sigma to be 1. That's all you do. Again, examples might be coming a little later. And they give you a simple section 543. 543. 543. They provide you in the books a very simple example. You follow it. Step number 1 is calculate D1. You already know the S0. You're also given the X, you're given the strike price, you're given the current price, you're given the continuous return, you're given the volatility and the time to expiration, so you can calculate the D1. Then you calculate D2. So you calculate the D1, you calculate the D2, and then you do N of D1. Because D1 is normalized, that's what this normalization is doing over here. Because it's normalizing, you look at N D1 and just look at the probability for D1. And you look at the probability for D2. You just look it up the table from the one that we have. And after that, you just plug in. Plug in, calculate. And you look, this is page 138. For you, it's page what, 142 or 143? Which page is the example?
144.
144
Yeah.
is the example. It's a little table. It just shows you, hey, this is what it is, and this is one example. Usually, you can have it in every calculator. Oh, it's very easy to type in Excel and can get it ready-made in Excel. You just plug in the 5 numbers. You plug in the 5 numbers, and based on those 5 numbers, you get the result. Because I've been repeating many times, and the 5 numbers are very simple. S0, X, R, or RC, sigma, and T. And these are the 5 variables of the Black-Scholes formula. And these are exactly the same variables as the binomial model. So, let me see where I'm going to go back to write. Well, I can write over here. 5, 4, 4. 5, 4, 4. They got characteristics, but it's also interpretation. So what are the characteristics? Well, the first characteristic of the formula is that there is no element for risk aversion. A different way of saying it is the formula uses what we discussed at the very beginning of the binomial model, risk neutrality. The model implicitly assumes, or the value is based on investors being risk neutral. And the risk neutrality is based on the idea that you can construct a risk-free portfolio. And for risk-free portfolio, people are risk neutral. So if you can construct a risk-free portfolio with the derivative, investors are relatively risk neutral. So you got risk neutrality means risk neutral probabilities. Here is one of the key results. The meaning or interpretation of ND2, the interpretation is that this is the probability of being in the money. So this is the probability that you'll be that you will end up in the money. So this is the probability that the price will be above the call. So that's a very important interpretation. So that's the ND2. Okay? So this is the chance of being in the money. That's the probability. Well, what is X? X is essentially the strike price. Okay? And what is this part over here? This part over here is the discount factor. So this is the conversion factor to present value. So, hey, I'm going to get that kind of money, let's say $100. The present value of the $100 will be, I don't know, $98 or $97. So you take the present value of what you're going to get and you multiply it by the chance of getting that money. So what's the chance? Well, the chance is 70%, or the chance is 30%, or the chance is 40%, okay? So what's the chance of actually being in the money? And by being in the money is to get the exercise price, okay? So this is the economic interpretation of the second part. Oh, there's a chance of 60% of getting in. And that's what ND2 is. So when you calculate the D2, what's in the example ND2? What's the example? So what's the chance of the stock ending up in the money? What's the chance? In the example on page, what's going to be? 143 or 144? What's the probability? Anyone, why are you looking at me? You gotta look at the book and read it off the book. What's the number? You just, it's, yes, 46.8%. So there's a chance of 47% that you'll end up in the money. If it's 47%, this means that there is a chance of less than a half of being in the money. Well, what does it mean, the chance of less than a half being in the money? Means that you're probably the current price is below the strike price. If the current price is equal to the strike price, the chance of being in the money is about 50-50. If the strike price is very high, the chance of ending up in the money is extremely low. Okay? And if the chance is 46% of ending up in the money, this means that the strike price is just a little above the current stock price. Okay? Well, what's the current stock price in our example? What's the current stock price? The current stock price is 125.94. and the strike price is 125. So they are very, very close. So with a probability of close to 50%, you know that you're just about close to 50%. Well, how could it be this price to be higher, this price to be lower? Is the difference is, well, how long is the option? The option is about 1/10 of a year, so it's over a month. So you need to convert to present value. I don't want to get into that, but the idea is, hey, if the chance is 50-50, probably current price is very close to the strike price. Okay? Let's see what else we got here. Risk neutral probabilities. Okay. Okay, so I got the D1 term over here. Let's see, S of ND1. Let's try and do this. S0 times ND1. That's S0 ND1. All right, I don't want to get into this too much because it's a little bit SND1. ERCT. Okay, ND1. Let me see what else I got in here. Probability, the expected payout of the exercise. Okay, the probability will be paid in expiration. I already covered that one. Formula, the lower bound. Again, they got this whole thing for the lower bound. This is on page 141. The lower bound of a European call, and the short answer is very simple. When you plug in the formula for the lower bound, you will get that it is basically satisfied. So when you have an European call, when you plug in to this formula, the lower bound for European call will be satisfied. So that's very simple. The lower bound is the higher of 0 and the present value S0 of X times E minus RCT. Well, maybe it's a big T over here. Big T. So when we look at this, it turns out that these are perfectly satisfied. So it's not a problem, meaning the formula still obeys the rules for the lower bound. So that one is clear. So that's the simple one. Next one is what happens when t equals 0? When t equals 0, in other words, as we get closer and closer and closer to expiration, this formula, when t gets close to 0, when t gets to 0, what happens? This becomes e to the power of 0 is 1. So this whole thing reduces down to 1, and over the calculation, they got it fairly simple and straightforward. They use a lot of stuff. It's a very, very advanced and complicated math. When they use it, it basically tells you that it's simply reduces again to the intrinsic value. It reduces to intrinsic value. Unfortunately, it just have very complicated math. You can see page 142 for you guys is page, what page? 147. So we're 5 pages of difference. They just calculate D1 and they see what happens, and a lot of things. The math is complicated because you're turning into limits. You need to use, it's called L'Hopital's rule. It's way too nasty and complicated because T here turns out to 0, and this one turns close down to 0. So it's very, very complicated. So the basic idea is, hey, when T gets down to 0, the formula reduces to the intrinsic value, and it's in the extreme gives us the correct answer. That's what they're asking. Another example here is, well, what happens, number 3? What happens if S0, or actually ST at one point becomes 0? What happens if the price is 0, or S0 is 0? What happens if the current price turns out to be 0? In that particular case, the company is dead, the company is bankrupt. And if the company is bankrupt, the call is worth how much? The call is worth 0. So we have to see if it's true that if S0 is 0, the call is worth 0. And basically you get that stuff over here. Again, I don't want to get into that, but from the D2, you're going to get that the stuff is 0. These are just standard calculations. What happens when sigma is 0? What does it mean sigma to be 0? What does it mean sigma to be 0? Huh? Yes, sigma 0 means no volatility. And no volatility basically means what? What's the interpretation of no volatility? No volatility simply means no risk. And no risk simply means risk-free. So if it's risk-free, when you plug in the formula, you should simply get the risk-free return. You shouldn't be getting anything more, and you shouldn't be getting anything else. And that's exactly what happens. So, that's exactly, again, they provide you. Number 5, what happens if X equals to 0? What does it mean X equal to 0? What does it mean the strike price is 0? The strike price is 0 means that you can get the stock for free at 0 cost. So any option which has a strike price of 0 will have the value of the stock, the value of the stock, the value of S0. So you're going to get the value of S0. So you plug in for X equal to 0, you should be getting 0. Well, if X is equal to 0, this whole term disappears, okay? And this D1 probability turns out to be 1, okay? This is the probability of being 1. And then the formula reduces to S0. Again, for each one, you can simply plug in, well, what happens if interest rate is very high? What happens in time goes to 0? S0 goes to 0. So you basically can plug in for each one of them to see what happens. And the last one they have here is number 6, when the return is 0. And when the return is 0, meaning the risk-free return, RC is 0, is not a special case. Nothing really happens, okay? It's not a big deal. You basically, this term will disappear and you're not going to have discounting. You simply have zero discounting. So when this becomes 0, this whole term will become equal to 1. The discount factor will be 1, and this is the same as, oh, interest rate is 0, we are not going to be discounting at all. This is the case today, where short-term and mid-term interest rates are practically 0. There is no major change in that. Okay. Again, we're going to do the same thing now by looking section 5 at the variables. Which are the variables in the formula? So, five variables. So, the variables are stock price. What's the next one? What's the next one? Page through. Exercise price, X. Continuously compounded risk-free rate. Volatility. And the last one?
Time to expiration.
Time to expiration T. So, 551 is S0. So, the ratio between the stock price is called the stock price and the exercise price. Let me see in what ratio. The relationship between stock price is often called a delta. This is between stock price, this relationship, and the call price. Is called the delta. Delta will be giving us the hedge ratio. And from the formula, something very interesting shows up over here. S, the price is only related in the first term. So, if S goes by 1 unit, the call is going to go by. So, if the price goes with $1, how much is going to go up the call price? The stock S0 goes $1. How much goes the call? How much? If this goes by a unit, that's the one, ND1. ND1 is the delta. The delta. And the delta is representing by the hedge ratio. In other words, delta gives you, we call it the sensitivity sensitivity to stock price. So, each variable, pay attention, each variable will have a sensitivity. So, the call will have a sensitivity to the stock price. If the stock price changes by $1, how much is the call gonna change? If the strike price changes by $1, how much will the call change? So you have sensitivity to the stock price, sensitivity to the strike price, sensitivity to the interest rate, sensitivity to volatility, and the last one is sensitivity to time. So delta gives you the sensitivity to the stock price. And this is essentially the meaning, the interpretation of the hedge ratio. Okay? So let me just provide a kind of like a very simple example. If the sensitivity is 0.5, this means when the stock goes up by $1, the call is going to go up by $0.50. If you want to be perfectly hedged, this means that you're going to have 2 calls for 1 stock. Okay? Well, there it is. So the sensitivity gives you that you got to have 0.5 stocks for the number of calls. So for 1,000 calls, you need 500 stocks. Okay? Well, if it's 0.3, it's the same thing. For 1,000 calls, you'll need only 300 stocks. And it's simple as that. So this tells you the number of shares to stay hedged, to remain hedged. Of course, it happens that delta is, well, could be also the border 0 and 1. Theoretically, it is between 0 and 1. So delta can't be more than 1, obviously. And delta can't be 0. When the stock goes up, the call is going to go up. So when the stock goes up, the call will never fall in value. When stock goes up, the call is going to be up. So it's a positive number. But if the stock goes by $1, the call can't go by $2 or $3 or $4. It's going to go by a fraction between 0 and 1. So that's one simple interpretation. They give you a very simple chart over here. And the chart is starting at 75. So when you're at 75, the call price is going to be very, very, very low. And it's going to rise very slowly. As it starts going in the money, it's going to start rising very fast. And it's going to rise very fast, close to a 45. If this is here the strike X, this is the time value, and it's going to start rising. So this is basically the price. That's figure, for me it's 5.6. Is it for you the same figure, 5.6?
150.
On page 150,
Yes.
what's the figure, the number?
5.6.
Okay, so it's figure 5.6. So on my textbook it's the same. Well, here's the next thing. What about the delta of a call? How fast is changing? How fast is changing? That's a lot trickier one. This is X over here. If you're far out of the money, the delta is going to be very low, and here's the trick. It's going to change very, very, very little. So early on, the delta's got to be very, very low. It will begin to rise, and let's see what happens next. it will rise, it will begin to steepen around X. And around X, we're going to have an inflection point. So here, the curvature is on the upside. And after X, the curvature is on the downside. So here it's curving up. Okay? So from the center, we say it's concave. On the other side is convex. Where the strike occurs, the curvature from being on the up becomes the curvature on the downside. Okay? So here we like to say that the delta accelerates. The delta accelerates. The delta rises faster, and here it decelerates. Here the delta increases. So he increases at a rapid, at a higher rate, and here increases at a decreasing rate. Okay? So that's a key. And now we're coming to the next major concept, and that's the concept of the gamma. Let me see where I'm writing this. Gamma, we can sometimes use the big G, is simply defined as the change in delta. In other words, gamma is defined as a change in delta. So let's try to provide examples so you can understand what we're talking about. Over here, when the price is 80, the delta is 0.1. And over here, when the price is 90, the delta is going to be, I'm picking a number, 0.15. Okay? So, if you have 1,000 calls, you need how many shares to stay hedged? How many shares to stay hedged? How many?
100.
Remember, delta gives you the number of shares for each call. So if it's the delta is 0.5, you need 1,000. You need for 1,000 calls, you need 500 shares. Here, for 1,000 calls, you need how many? How many? Do I need a chair? I need to get a chair and relax.
Too many.
How many?
100. 100. 100.
Oh, wow. 100
0.1
shares. Okay, we need 100 shares. Okay. Well, what happens next? The price goes, so we need 100 shares when the price is 80 to remain hedged. Okay? Well, when the price goes to 90, you need how many shares?
150.
You need 100 for the same 1,000 calls. You need 150 shares when the price goes to 90. Okay? So, when you keep the number of calls constant, when the price goes up from 80 to 90, you need to buy extra 50 shares. Well, that's the vicious cycle. That's the destabilizing part that I was explaining a few times ago, that the price of the stock goes up. You need to buy more shares to stay hedged. And the buying of shares, when you have to buy extra shares, it's going to drive the price to 95. Okay, it's going to drive the price higher. And then you need to buy more shares. Okay, so when the price goes, let's say, to 100, how many shares are you going to need? Well, here's 100. You're probably going to need now 0.2, about. I'm just making the numbers up, okay? So when it goes to 100, you need to have 200 shares, okay? So the problem with the delta hedge is that it constantly keeps changing. It was 100 shares, meaning 0.10, now it's 0.15, now it's 0.20. Well, the difference between 0.10 and 0.15 is gamma. Okay? So gamma, which is the change of delta, tells you the risk of being or remaining unhedged. The risk of remaining unhedged. Risk of unhedged. So, when gamma is large, small changes in the price will require major changes in your portfolio, will require a lot of portfolio. When the gamma is small, in other words, when you're deep out of the money or deep in the money, you don't need a lot of adjustment. You need a lot of adjustment where you're close to at the money. So when you draw the picture of the gamma, that's figure 5.9. That's figure 5.9. Let me see where I'm going to do this. Okay, here is the gamma. When you have the strike price, the gamma is going to be rising and then falling. In other words, gamma is very small far out of the money, very small when you're deep in the money and when you're deep out of the money. And the gamma is relatively high when you're close to at the money. So when you're close or at the money, you need major adjustments. Small changes in the stock will require large changes in the portfolio, will require a lot of, we call it dynamic hedging. Let me repeat that again and write it. Dynamic hedging. So small changes will mean a lot of dynamic changes. So gamma tells you the risk of remaining unhedged, the risk of remaining unprotected. If the stock market jumps today by 2%, oh, are you going to be exposed to a lot of risk or going to be exposed to little risk? If you do not hedge, if you don't hedge dynamically, if you just remain the way you are, okay, it will tell you what your risk is. Okay. And you also see what is the gamma of a call. You see it on page 147. It's going to be 152. It's E minus whatever. That's, let me see which one expression is this. ED1. It's a fairly large expression over here. Don't want to get into that. It can be easily calculated. Okay, let me do this figure 5.8. Let's do the figure 5.8 because it's tricky and it needs an explanation. delta of a call. So, delta of a call. So, suppose the delta is like 0.4, and I got, let's say, 50 days remaining. This is 40 days remaining, 30 days remaining, 20 days remaining, 10 days remaining. So, you got times t, time to expiration, okay? And if it's time to expiration, you got some delta, okay? And then the question now becomes, well, what happens to the delta as you get closer and closer and closer to expiration, okay? Well, what does it mean, delta being very high? What does it mean, high? Let me try to write. Here, the delta is high, okay? And here, the delta is low. What's the meaning of high and what's the meaning of low for the delta? What does it mean? It means, for high, means in the money. And for low, delta means out of the money. So, you're in the money by, let's say, 10%. 10% in the money simply means that the strike is 100 and you are 110. So the price is 110, the strike is 100, you're quite in the money, okay? And you got 60 days left. As you are moving closer, got, let's say, you have, let's try to do this. 100 is the strike price. 110 is the current price, okay? And you got 60 days left. What's the probability? What's the probability of ending in the money? What's the probability of ending in the money? Well, it could be like 60%, okay, for 60 days. Well, if it's 30 days, what's the probability? Is the probability going to go up or down? You got a same difference, all right? So you're in the money by $10. What's the risk of going out of the money within the next 30 days? And the answer is, it's lower. So in 30 days, to remain in the money, probably the risk is going to be 70%, okay? And if it's only 10 days, the risk is going to be 90%. So if you're well in the money, if there is 1 minute left, you're going to be remaining in the money. If you're deep in the money, if there's only 1 hour to trade, the chance is almost 100% you're going to remain in the money, okay? If you got to trade 1 day, again, the chance is close to 100% that you're going to remain in the money. If, on the other hand, you got 5 years to trade, what's the chance of remaining in the money? What's the chance? You got 5 years to trade. What's the chance of being in the money? Well, it's 50%. Close to 50%. So, if the current price is 110, after 5 years it could be 200, it could be 50, it could be 70. So, the chance of being above and below is close to 50%. So, if you're very, very far into the future, chances are about 50-50 that you're going to be in the money or out of the money, okay? But if it's just 1 minute, the stock is 110, okay? And it's only 1 minute left and your strike is 100. Within 1 minute, what's the chance of being in the money, of remaining in the money? The chance is close to 100%. So as you are moving closer and closer in time, if you're in the money, the chances increase that you will expire in the money because there's little time. On the other hand, if you're out of the money, as you move closer and closer and closer in time, the chance of remaining out of, in other words, you bought an option, the current price is 80, the strike price is 100, you bought it 2 months ago, and today you're still at 80. What's your chance of getting in the money? Well, relatively small, maybe 20-30%. Then there's 1 week remaining. What's the chance? Well, the chance is maybe 5%. Then there's 2 days left. So if you're $20 out of the money, as time gets closer and closer to expiration, your chances get smaller and smaller and smaller that you will actually end up in the money. Well, that's what it tells you. It tells you that if you're far away, chances are almost 50-50 that you're going to be in the money or out of the money. But if there's only 1 day left, chances rapidly increase that you're going to either end up in the money or out of the money. This is called a bifurcating probability. All right. You guys, you're familiar with football games, soccer, right? You guys play soccer, at least watch it on TV? Yeah? All right, so you start, you got 90 minutes. You got 90 minutes in the game, right? And you guys luckily score in minute 1 and score in minute 4. So the score is 2-0, right? What's your chance of winning? Pretty good, maybe 70, maybe 80%, okay? Now, here, at the end of the first period, it's still 2-0. What's the chance of winning now?
80.
So,
90
it's higher, it's 80%. Well, what happens?
ครูเมื่อคืนเลย
There are 15 minutes left, and you're still 2-0. What's the chance of winning? Well, 90%, 95%, right? And now, 5 minutes before the game, the score is still 2-0. What's your chance of winning? It's close to 99%. You say, oh, the game is sure. There are 5 minutes left, we're already 2-0. They don't have a chance even for a draw, okay? So, this is the same thing. 2-0 means you're already in the money and there are 2 weeks left. And then you're quite in the money and there's 1 week left. And there's 1 day left. And there's 1 hour left. So the closer you get to the close of the game, which is in this case expiration, the higher is your chance. So here the chance may be 60%. Here the chance becomes 70%. Here the chance becomes 90%. And here the chance is already 99% that you're going to win the game. It's exactly the same. As you get closer and closer to the end of the game or to the expiration, the chance of, if you're in the money, to remain in the money gets higher. In other words, if you're leading in the score, the chance of winning the game gets closer to the end of the game. Okay? Well, it's exactly the same here. And this is if you're out of the money. All right? Is if you're 0 and the opposing team is 2, you're out of the money. So the probabilities are actually symmetric. If your chance to win 5 minutes before the game is 99%, for the opponent the chance is 1%. So these add up. So that's exactly how this works. So with a long time, the chance of out of the money is close to 50%. But as you move closer, you're moving either to 0 or you're moving to 1. You get more sure that you're gonna make money, or you become more sure that you're just gonna lose money. So here, the situation becomes almost sure as the probability goes to 1. And here, it becomes almost hopeless. So, this is a big hope, there is no hope here. And the certainty increases and the hopelessness increases. Okay, is it fairly clear? I
Clear.
hope so. You guys get tired? Let me see what else. Oh man, we got exercise price. Okay, let's take a break here.